Welcome everybody to episode 16 of Games with Go, where we're going to continue the Evolving Picture project. And we'll talk about genetic algorithms today. So before we get started on genetic algorithms, I wanted to add a few more functions, a few more operations that our tree can have in it. Yesterday we just got some basic ones in so we could make sure everything was working the way we wanted to. So we're going to add some more. Quick change here. Let's make that lowercase to abide by Go conventions. And let's make this take in red, green, and blue nodes. And then we're going to, let's call these red node, green node, blue node. By the way, new microphone tonight. Let me know if it sounds better or not. So what we're doing here is we're going to have three equation trees, one for each color. Red, green, and blue. And then we'll draw them all together to get our final color. So we'll do red, green, blue. All right, that's all I wanted to do there. So let's go over to our abstract picture tree and let's start adding some more operations. So we've got plus. Let's go ahead and do all the obvious ones. We'll do plus, minus, multiply, and divide. So I'm gonna copy paste to do that to save time, which is a dangerous habit you might not want to copy. So it's going to follow the exact same pattern as plus, except the eval will do subtraction instead. And then when we print it, we will print out that we're doing subtraction. Multiply will follow the same pattern. Multiply, multiply. Then we'll do divide. Divide, divide. Okay. Then another one I'd like to add is atan2, which if you're not familiar with what that is, you can look it up on Wikipedia. Let's see. Atan is short for arctangent. So you can read that on your own time, but it's going to make some neat patterns for us, I hope. Okay, so in this case, this is going to be very different. This will use the math library's atan2 function. And we'll pass it y and x. And it expects 64-bit floats, so we have to cast. Okay, and here we'll just say atan2. Okay, so yesterday we made two different kinds of leaf nodes, x and y. We're going to add a third, which will just be a constant. And this will be a struct. And we're going to say that it's got a leaf node in it. Even though leaf nodes don't have anything in them. It's just an empty struct. This will be important later because it's going to this will automatically give op constant functions related to leaf nodes, which we'll see that later tonight, why that's important. And then it'll have some value. That's a float 32. And we just return that value to evaluate us. How is the new microphone? Is it better, worse, same? How do we get a string out of our float? Okay, so we have to use the string converting package. It's got a format float function. So let's talk about what all that does. So there's not an obvious way that one should print a float because they are a lot of decimal places if you print the whole thing. So let's see. Yeah, so F says basically it's sort of the default formatting style. And then the precision and bit size. So this is, we're telling it it's a 32-bit float. And I think that's telling us to print 3 decimal places, which maybe we want more. Let's make that bigger. And then we need to import string conversion to get that library. That's one of the built-in Go libraries. Okay, so now we have constants. What else? So let's do, where's sign? Along with sign, let's do a couple more like it. We can do cosine. And then we can do regular arctangent. So arctangent comes in 2 forms. Arctangent 2 takes an x and a y, and regular arctangent just takes in 1 number, just like sine and cosine. All right, now let's add a fun one. So if you were here for the simplex noise stream, then you will be able to import the noise library we made. If you weren't here for that, then you can just leave this next operation out. It'll be no big deal. You can add it later. Okay, so that's going to give us our noise library. And now we can make noise, simplex noise, one of our functions, the same way we make plus one of our functions. So let's give that a try. So call it op noise. It'll be a double node because it takes in an x and a y, just like plus and minus do. And so for x, we evaluate the left side of the node. And for y, we evaluate the right side of our node. And then I'm going to multiply this. I'm going to scale the noise so that the noise will be between -1 and 1 approximately. So multiplying by 80 is going to make it between about 0 and 2. And then we'll, is that right? 0 and 1. I think this will make it between -1 and 1. We can check it later. Type op noise strict. And we also need to print it. So remember that we have to, for any operation we make, define all the methods that the node interface specifies. So it will be a node itself. All right. Okay, so now we have a bunch of operations available to us for our picture equations. We'll probably add some more later, but that's good for now. Let's test a few of them. Let's put some noise in there. And let's do an A10-2. And let's see. So I'm just building up a tree haphazardly here. We'll see what it looks like. So let's see, did we get everything in there? No, let's make that Y, and that will be signed. So I think what we have here is plus, we're going to have sine of a tangent of x in noise plus y, I think. Let's give it a try. Just start with black and white by passing the same node to all of them. This is lowercase now. All right, let's see what we get. All right, interesting. Let's try a variation where we didn't get noise leaf nodes. No difference. We can make this multiply. There we go. Now we're seeing, I think A10 was basically destroying our noise completely. So you see how we can make all sorts of different strange patterns pretty quickly just by changing the operations around. So typing this all out by hand is kind of tiresome, so we're not going to do that anymore. We're going to start building those automatically. Which brings us to genetic algorithms. So what are genetic algorithms? They are a type of optimization algorithm. They are called a meta-heuristic. They are one of many kinds of meta-heuristics. And what that means is when you're trying to optimize something, a meta-heuristic will find an answer, but not necessarily the best answer. You hope it will find something good, but not necessarily the optimal solution to a problem. So they're good for problems where finding the optimal solution is impossible or impractical to do. So what people talk about is, with this is you could talk about a solution space. So you can imagine you're trying to find an optimum solution to something. Let's take something really simple. Like let's say you're trying to find the optimum amount of fuel to add to a fixed amount of air to get the biggest explosion, right? You would do this in car engines and bombs, I guess. So if you talk about the fitness of the solution or how good the solution is, this would be like energy, right? How much energy do you get out of the reaction? And then the solution space would be, you know, how much fuel? How much fuel do you add to the fixed amount of air? And that's going to look, you know, something like this, right? If you don't have enough fuel, you get a smaller explosion. If you have too much fuel, you get a smaller explosion. And where the mixture is stoichiometric, you get the biggest explosion. So problems like this are pretty easy to optimize, and you can use an algorithm called a hill climbing algorithm to find the optimum solution, assuming you didn't just look it up in a book, of course. So the way a hill climbing algorithm works is you pick a random place to start. So maybe you try this. And then you change your solution by just one element. You just change one thing about your solution. So in this case, you could try a little more fuel or a little less. If your change results in a better outcome, if you climb up the hill, then you keep that change and you make one new change. And you do that iteratively over and over and over until you get to the top, right? And if you try to make that change again, it gets a little worse, so you don't keep it. So you end up here and you find the optimum solution. So that's great. But lots of problems are harder than that. For example, imagine you were trying to build the fastest possible bicycle for some particular course, right? So now this is going to be speed. And of course, a real solution space for something like a bicycle would be many dimensions, and I'm just showing 2 dimensions to simplify. So say that this was something like mass, right? And what we find, maybe we'll pretend the solution space is something like this. So what this could represent is maybe if you don't have enough mass in the bicycle, it falls apart and you don't go very fast at all because you don't finish the race. And then as you get too much mass, of course, you get heavier and can't go as fast up hills and so on. So a hill climbing algorithm, if you ran it on something like this, let's say you started here, it would start changing one aspect about the bike. And when it tried to change mass by making it a little lighter, wait, have I done this backwards? Yeah, that's right. So as you make the bike heavier, it starts staying together longer. So you get faster and faster. But then as you add more weight past this point, it starts to get worse. So your hill climbing algorithm gets stuck right here at a local maxima. That's a word you'll hear a lot. And so the hill climbing algorithm by itself is no good for finding the best solution to this problem. As we can see that there's another hill that's even higher over here. but the hill climbing type of algorithm can't get there. So genetic algorithms is one kind of algorithm that can deal with this type of solution space. There are many others, but it's a fun one. And the way it works is you start with a random population of solutions. So instead of starting in one spot, draw a new curve. You might start in quite a few spots, right? You got a random population of bike specifications, and they've got different masses. And then you start iterating, and you take your population, you see which ones are fastest, right? So maybe you pick this one, and this one as your top performers, and you drop that one and drop that one. And then you mutate the specifications. You make some small changes to the specifications of all of these. And you might also mix and match parts of their specifications, right? And so in humans, we have DNA, and that's what this is modeled after, is life on Earth. Right, so you might have one human with some DNA that looks like that, another with that. And this is a specification for how some part of your living thing works. And when they create offspring, you might take parts from each, right? So your offspring might get the first couple parts from one, and then the last couple parts from another. And so this will cause them then to have some properties of each parent, or some mixture of those properties. And so if you do something similar with your optimization problem, you take some specifications for your fast bike and mix and match them above the good performers, you hopefully will get a few offspring when you create new ones, new solutions based on these, that are even better than the old ones. You won't always, it could be worse, that happens. And you repeat the process, right? Then again, you take your new best performers and kill off the old ones, survival of the fittest, and then create some new offspring, right? And so the idea here is that you get more random jumps by starting with a random population and doing this crossbreeding. You get more random jumps across a solution space, and so that hopefully you'll find the top of the biggest hill, though that is not guaranteed. If your genetic algorithm takes random jumps that are too big, you might skip over some of the highest peaks in the solution space completely. And if their jumps are too small, right, they may just wander around and get stuck in a local maximal and never get over here. So it can take a lot of tuning to figure out the right sorts of mutations to do and the right way to crossbreed different solutions in the population. So how are we going to make pictures with this? So we have equations that are pictures, or we have equations that make pictures, and they are trees, right? So our example from yesterday was plus sine of x and y, right? And say that's one of the pictures that you kind of liked. And maybe we have another picture that we kind of like. Maybe that's noise of multiply x, y, and y. So two things we need to be able to do to make a genetic algorithm is we have to have a concept of mutation, where we make occasional random changes. And that's easy enough, right? We could just do something like we cross out sine, replace it with a different random operation, right? That could be a mutation. That's very straightforward. But how do we do sort of a crossbreeding type thing? Well, one thing you could do is you could pick random parts of your tree. So you could say, pick this part here and this part here and swap them, right? Move that one here and this one here, which will give you two new trees that share some properties of your old trees. And with any luck, the images will also share visual properties as well. So if you like this one and you like this one, you might like even more some combination of the two. So that's what we're going to do, is we're going to have a way to build up random trees first. And then we're going to build up functions that can do things like swapping sub-portions of each tree to make new ones, right? And the final application will let a person look at a bunch of thumbnails of these pictures and pick, 2 or 3 or 4. We'll have to play with what's best, or the ones they like best, and we'll do this crossbreeding with them. Any questions about all of that? Okay, so feel free to fire away with questions while I'm continuing. Comment this out for now. First thing we're going to do is put together a way to make a random tree. And in doing that, we're going to see why we made these structs last episode. Because some of you might be wondering, what's the point of having these structs, leaf node, single node, and double node, when all we do is just put them in op_sign, right? Like, why doesn't op_sign just have a child node, right? Why is it using an embedding of the single node struct? And the reason for that is, while eval and string have to be particular to every single operation we do, right? Because the thing you want to print for sine is different than for cosine, and the thing you eval is different. We're going to write functions that operate on the tree structurally, like doing the adding of nodes and swapping of nodes around. And for those operations, it won't matter whether something is a sine or a cosine or a plus or a minus. All that matters is how many children does it have. 0 like a leaf node, 1 like a single node, or 2 like a double node. So by making these, we can make functions to add random nodes to the tree. And we only have to do write that function 3 times. Once for leaf nodes, once for single nodes, and once for double nodes. And then all of our operations will effectively inherit those because they have embedded that struct inside themselves, which will keep them all acting as nodes. So let's actually do that to see what it looks like. So our node interface will now add a new function that you have to satisfy, and that's going to be called add random. And it's going to take a node, and it's going to add it into a random location inside the tree. So let's see how we'll do that. Right, so we'll need to write this function for all 3 of our node types. So let's get started. Okay, so the leaf node case is easy. If you try to add a node to a leaf node, you have committed a mistake because you cannot add anything to a leaf node. It is the bottom of the tree. So we'll try to make sure that never happens. If it does, we will panic and spit out an error. So we will know immediately if we ever make this mistake. Done. So now we'll do single node. So here there's 2 cases. If the single node's child is currently equal to nil, so it hasn't been set yet, then all we do is take the random node that we're going to add to our tree and assign it to the single node's child. Right, so if we had a sine op and we added a plus operation to it, it would just make the single child of sine equal to a plus node. Now the other possibility is that single node's child has already been assigned, in which case we use the magic of recursion and just pass that node along down to the child. Oh, single. And that's it. So one more time for the double case. So this one's going to be a little more complicated. Since we're doing it randomly, if we had a plus node, we have the choice of adding it to the left side of the plus or the right. Since we want to do it randomly, we should pick randomly between adding it to the left or right. So what we'll do is we'll get a random integer from the built-in rand function. And we'll need to import math rand to do that. And so rand.int n2 is going to give us a number between 0 and 1. So if r equals 0, we'll do the left side, otherwise we'll do the right side. And then we'll do the same logic in each of these as we did for the single node case. So if the left child is nil, then we just set the node equal to it. Else we use the magic of recursion to pass it on down the tree. And then same logic here for the right side. Okay, so now we have functions that can add random nodes to our tree. We're also going to need some functions to spit out some random nodes. So let's do a get random node function, which will return a node. So how many different nodes do we have? So we're going to make this do non-leaf nodes only, and we'll see why in a minute. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9. It's like 9 operations currently. So we'll say rand equals int in 9. And we're going to do a switch statement. And I don't know if we've done these on stream yet. I think we have a little bit. It's just like a if statement, but a little bit nicer when you have a whole bunch of cases. So we'll get a random number between 0 and 8. And we'll just return a different operation in each case. So we've got op plus, minus, multiply, and 2. cosine. And then noise. So that should get us, how do we minus? What do we call? Oh, of course. Everything starts with op. I guess if we get here, we should panic. Because that would mean we messed up and did not match our random integer with our switch statement. Okay, so now we're going to do the same thing, but for random leaf nodes. Of which we only have 3. Okay. Cyrusaf asks on chat, are those blue switches? I don't know. What is a blue switch? Okay, so we'll learn something here. So when I made the op_x and op_y, I just did a type alias to leaf node. But when you do that, you do not inherit the functions attached to leaf node. So we need to change this to be like that. So now we are embedding leaf node in op_x and op_y, and that should, yes, solve the problem. And then for op constant, a little special case here, we need to give it a random value. And we can do that with ran.float32. To get us something between -1 and 1. Oh, are those blue switches on my keyboard? They are, if not blues, something close. It is a clacky keyboard for sure. I really like them. I used to think I could type a lot faster on a clacky keyboard, but I figured out that is not correct. I tested myself. It's the same, but I like it better. Why aren't we happy? Leaf node literal. Oh, like that. Okay. And then again, if we get here. Okay, so now we can get some random operations and leaves, and we can add them to our tree in random orders. But there's one more thing we need, which is when we're building the trees, we're going to be picking random operations first, right? So we're going to have maybe plus, and then minus, and then sign. But to finish our trees, we're going to need all of the bottom parts to be leaf nodes, right? At some point, we have to stop. We can't just go forever. So this will have to be, these things will either have to be x, or a constant, or y. So as we're building our trees, we're going to have to kind of decide how many operations we want to add. And then when we've got enough operations, we need to finish it off by filling in the rest with leaf nodes. So we need to know how many leaf nodes the tree needs. And that won't be predictable ahead of time because the nodes we add are random. And some of them have 2 branches and some have 1. And later we're going to have some with 3. So there are a few ways to solve that problem. The way I have thought of is to write a function that gets info about the tree, about how many nodes there are and how many leaves there are. I think we're going to need to know both those things eventually. So we're going to do a function called node counts. And I don't think that needs to take in any parameters. Yeah, so node counts won't take in anything. But it will return 2 things. We're going to get the node count and the nil count. These will both be ints. Okay, so when we call node counts on a tree, we're going to get back how many nodes there are and how many nil pointers there are. So that'll be like these guys before they're filled in. Minus will point to the left and right. Both be nil, and sign will be nil. So that'll tell us how many leaves we need when we know how many nil pointers there are. All right, so again, we only have to do this for the 3 structural structs. Pear Treer on chat asks, why do we need the node count return value if you only care about the nil count? So for now, we're only going to care about the nil count for this problem of how many leaf nodes we have to add. But later we might want the node count in order to do some of the crossbreeding things, because we're going to have to pick a random node in the tree. And one way to do that would be to pick a random number between 1 and the number of nodes in the tree, and then walk the tree for that many iterations to pick a node. So to know how many nodes are in the tree, we'll have to have that node count too. And since you're sort of doing the same thing, you're walking the tree to get this data, we might as well get both at once, since I think we're going to need both. I could be wrong, but I think we'll be glad to have both. All right. Okay, so for the leaf case, this is really easy. We have, if we're a leaf, we have 1 node, and we have no nil pointers, because we do not have any nil pointers ever, because we are a leaf. Okay, single is a little more complicated. If the single's child is nil, then we have 1 node, ourself, and we have 1 nil node. But if our child is not null, So we're going to get the, that means we have a child node. So we're going to get the child count and the child nil count from our child. This should be node counts. Okay, so we call node counts on our is equal to. We call node counts on our child, so we get the number of nodes that our child has and the number of nil count that our child has. And then we add 1 for ourself to the child node count and return the child nil count. Okay, so if that doesn't make sense, what would be happening there is, say you passed it to plus, right? Its node count would be the node count of the, oh, sorry, sign. This was like a single node example. Sign's node count would be 1 itself plus the node count of its child tree, which in this case would be 1, so a total of 2. Sign and x are the 2 nodes. And the nil count in this case would be 0, because it's just returning the nil count of x, which is 0. No nil pointers. A little more complicated than that is a double case. And by the way, this where I'm naming the return values, that's never necessary to do. It's sort of a documentation feature, so that if someone looks at this in documentation or IntelliSense, you have more of a clue of what those things are, rather than just seeing that it returns 2 ints. Okay, so now for the double case, we're going to keep track of a left count, a left nil count, a right count, and a right nil count. Those will all be integers. Those will all be 0 because Go guarantees undefined variables you haven't assigned are starting at 0. So if we have no left child, then left nil count equals 1, right? Because our left child is nil, so left nil count is 1. And our left node count is 0, because it was nil. Left child. But if we do have a left child, then the left count and the left nil count equal node.left dot node counts. Maybe I should have called that node the whole time. All right. Let me do the same thing for the right side. Okay, so now we know the node counts for the left and right sides. So now we add 1 for ourselves. Add up the left and right. And then for the nil counts, left nil count plus right. All right, and that's it. And now all of our operations will inherit the node counts and add random functions that they need, because they embedded the appropriate struct. Okay, so that's kind of a fancy use of interfaces and struct embedding here. All right, now that we have these functions, we can build up an image equation automatically, a random one. So let's do it. Okay, so first thing we'll want to do is we'll make our abstract picture tree red. We'll start it out, we'll make a root node. What do we call it? Opper node. With a random node. We'll do one for R, G, and B. And then we'll pick a random number for how big to make it. So we can say maybe up to 20 nodes. All right, 0 to 20 nodes on top. And then we'll loop. And we'll just keep adding. APT R. We'll keep adding a random node. Oh, we need to import math.random in this package too. Okay, so let's do the same thing for green and blue. Okay, so this will give us 3 random trees, but they'll have no leaves yet. So what we'll want to do is we'll get our node counts. If node count is 0, we can break. Otherwise, we'll add a random leaf. We'll do that same thing for green and blue. So red, green, and blue. So that should give us 3 filled out trees. So now we can pass the red, green, and blue trees to our function that creates a texture. And it should draw it. Let's see what happens. We have a bug. We tried to add a node to a leaf node. So I think our add random is perhaps not clever enough. Okay, so we need to check to see Okay, I'll check it. So the problem we have here is add random picks a random way to go. And it may pick a leaf node to try to add to. So to do this properly, so let me show you what's going on. So we could have a partially built tree that looks something like this. Right, we have one open space for a leaf node, but add random is randomly picking the left and then randomly picking to add to the right and hitting a leaf node and failing. So what we need to do ultimately is have a backtracking system where if we try to add a random node and we can't, we back up and then try to go the other way. We don't have time to do that tonight, but we're going to need to do that. So we'll put that on a to-do list. We're going to need to do backtracking on add random. What we can do for now is remove this panic. We'll keep a print line in there so we don't forget about it. Import format. And what will happen, because this loop keeps going until nil count 0, it'll just keep rerunning it until it gets to where it needs to go. Until all of the nil pointers are filled up with leaf nodes. So chat says line 170. Oh, thank you. That's why you don't copy paste. Red, green, blue. Red, green, blue. Okay. All right, we got something. And you can see we're wasting a lot of time trying to add nodes to leaf nodes before we fill it up. But that's okay. Okay. Here's another thing to know about programming. You notice if I run it again, I get the exact same thing. The way random numbers work on computers is they are pseudo-random. There's just an equation that spits out random numbers. And it'll do the same random number every time you run the program, unless you give it a seed. So if before you use rand, you seed it, with some number, it'll pick different random numbers, right? So I seeded it with 5. Now we get something new. That's pretty cool looking too. But now it's still going to be the same because it's always being seeded with 5. So the trick, which is fine for games, not good enough for cryptography, is to just give it the current time. So you can do that in Go with the time, built-in time library. And that's basically getting the like current elapsed seconds since 1970, I think, or some old date, as a single number that we can use as the seed. And so now every time we run it, we get a new picture. We get a new random equation. It's pretty cool. Then another cool thing we can do is once it's all done, we can print them all out. All right, so that's our image, and these are the 3 equations for red, green, and blue. Oops. That produce it. So at some point in the future, we could save this text and use it to load a picture that we really liked later by just parsing this and creating the tree again from the text. Another idea I have that we might do when we get to doing OpenGL is we should be able to use the abstract syntax tree to spit out a shader program that will draw these. And as these things get really big, if you get to like hundreds of nodes, it takes a long time to draw them, especially if you use a bigger image size because there's more pixels. Because it's having to iterate through this tree, which is pretty slow. But if you spit out a shader program, you could do videos of this, which I think would be really cool. So that might be something in the distant future. All right, so this gives you lots of stuff to play with. I'll give you guys some homework here. Which is add some new operations. Right? It's really easy. You just have to define the eval and string functions, and you've added a new operation. It can be anything you want. A little bit harder homework. Add an operation that takes 3 arguments. Right? And to do that, one example you could do is you could do lerp. If you remember lerp from before, linear interpolation. That takes 3 arguments. So you would need to make a new type of node, a triple node, and add the insert random and info or node count functions for it to do that. But it's not too bad. You can follow the same patterns from the other. So you can play around, have a lot of fun with this. You can change the sizes that you generate for your random trees and see what kind of crazy images you can get. And then what we'll start working on next is we'll draw a bunch of these like as thumbnails on the screen, like say 9 or 12 maybe, and then let us be able to click on ones we like, and then generate a new population that crossbreeds the ones we liked into new images. And then we can do that over and over and see what kind of stuff we can build up. All right, any questions before we sign off tonight? Well, I'm just going to generate random pictures for a while. I had another homework idea. I'm going to add that before I go. So you can actually make time one of the parameters in eval. And if you keep redrawing or recomputing the image every few milliseconds and passing that time, constantly increasing time, you can make a video. And yeah, you could make the video loop potentially if you do it right. You will probably have to make the image pretty small to get a good frame rate. Like 320 by 200 or so, depending on how fast your computer is. But this does work if you can figure it out. So it's another fun one. Peartreer asks on chat, do we plan on doing some work on game servers, maybe using gRPC or something, and how to handle games on a network? I assume that gRPC is a library for doing remote procedure calls in Go. I do want to do some multiplayer stuff. I'm thinking we'll probably do multiplayer Pong because doing multiplayer stuff for action games anyway is really hard. So we want to keep it simple. And we'll probably do it more from scratch. We'll talk directly to sockets. We'll learn how to serialize our structs in an efficient way and learn how to do client-side prediction. So it'll be good. It's fun stuff to do. And it's pretty hard, but even multiplayer Pong can be kind of fun. It'll be a server client architecture. And one thing to keep in mind, if it is an action game, using things like RPC libraries may not be a good idea because you really want as little overhead as possible. Like games will often even pack a 32-bit floating point value for position into like 7 bits or something to make things small, to help reduce lag and stuff. Someone asked in chat if you use UDP for games, and it depends. If it's an action game like Doom, you almost always are going to use UDP because a UDP packet, it gets there quicker. There is no acknowledgement process or back and forth in the protocol, which saves a lot of overhead. The downside is you do not necessarily get your UDP packets to the destination, so you have to deal with that. But for things like positions, if a position's moving fast because someone's running around on a map or something, you almost always need to use UDP. A more strategic or RPG type game, you could probably do without it, now that the internet is much faster than it used to be. All right, guys, I'm going to sign off. Thanks for joining. Keep in mind, you can subscribe to the channel now, and you won't have commercials if you do that. And if you have an Amazon Prime membership, you can use that to subscribe for free. And if you have friends or family members who are interested in programming, please let them know about the stream. All right, I'll see you next time. Bye.